Now we want to talk about partial pressures.
What we want to get into talking about here is gas mixtures. We're going to think about what really happens when a gas mixes. So a mixture is still just a gas, right, of just different types of molecules in there. And so if we want to characterize that gas, we can characterize it using the same properties that we've talked about before. So amount, we know that the total number of moles, let's just be related to total molecules, that would be just the sum of all of the molecules that we've added. So if we have, say, a purple, a blue, and a green gas, A, B, C, if we just add those two numbers of moles together, we would get our total number of moles. For temperature then, all the different gases are all mixed together, so all of the molecules are going to be moving around, bouncing off each other. So they're all going to have the same average kinetic energy, and they're going to be moving with the same, kind of zip as they fly around. So they're all going to have the same temperature. This is the same idea we've talked about back in chapter 5 about the idea that when two objects of different temperatures come together, they become the same temperature in the end. So all of the gases are mingling, so they're all going to come to the same temperature. Similarly with volume, this is unique for gases, but all of them have the same total volume because they all fill this same box, right? So if you have this mixture of gases, the volume of the purple gas is the same as the volume of the blue gas, right? A, B, and C all have the same volume because they're all in the same box. That's unique for gases, that they do all fill the exact same volume. Again, they're mostly empty space, so the molecules can just kind of intermingle with each other. The final variable I want to talk about then is pressure. And so if we think about the gases when them by themselves, we know that if we had, say, that same volume, right, the gas is just going to fill the volume independent of whether or not it's a mixture or it's by itself. It's going to fill that volume, and each gas is going to have its own pressure, right? There's a pressure for gas A, B, and C if they were by themselves. If we make a mixture, all of the gas molecules come together, we still have all the same relative numbers of the different molecules. And so they're all going to contribute to the overall pressure in the same way as if they were by themselves. So each gas, the purple gas, is still going to be colliding with the walls of the container in the same way that it was previously. And so there is a contribution to the pressure from that gas C. So all of these pressures are going to add together when we form a gas mixture. This is overall described by what is called Dalton's law of partial pressure, which says that the overall pressure of a gas mixture is equal to the sum of what are called the partial pressures of each gas. So here we have an expression for it. We can see this P, this under the subscript tot, that'd be the total pressure, which is the overall pressure of the mixture. So all of those different types of gases combined together, what is the overall pressure of the mixture of all these different types of gases. Then we have the P's that have the subscript A, B, and C. These are called partial pressures. And those subscripts, the A, B's, and C's, those would correspond to the names of the gases. Usually we use the chemical formula, so N2 for nitrogen, CO2, carbon dioxide. But here A, B, and C is just standing in for that. And the partial pressure is the pressure that each component gas would have at the same temperature and volume. So if that gas wasn't in the mixture, if those molecules were just by themselves in that same volume, what would the pressure correspond to for that particular gas? And then we can see that these just keeps adding together. We have that little italics, or ellipses, sorry, past A, B, C, because however many gases you have in the mixture defines how many terms there are. If you just keep adding more and more and more gases, there are more and more terms in this mixture. You can have 5, 10, 50 gases in a mixture. You just add up all of their partial pressures. So what's going on here is the idea that when we have, say, these molecules moving around in the gas, if we had, say, the gases when they're by themselves or when they're in the mixture, they still are moving around in the same way. And pressure is all about the collisions of the gas with the container. And so if your air molecules, say in this case, are moving around, they're colliding with the container in a certain way, and say you get a pressure of 2 bar. Well, when we put them in a mixture, those molecules are still moving around and still colliding with the walls in the same way. So you're still going to contribute 2 bar from those air molecules. The steam, when it's by itself, contributed 8 bar from all of its collisions. The steam molecules are still colliding with the walls, so you still get that same contribution of pressure. And importantly, because gases can be assumed to be ideal, we know that means they don't really interact with each other. What that means is that it doesn't really matter. The air molecules are bouncing around. They don't care that they're now steam to bounce around, steam molecules to bounce around on. They're just bouncing around like whatever. Okay, it doesn't matter when they are mixed together. The contribution of those molecules to the number of collisions is still going to be the same. Let's see using this in practice. So CO2 is added to a tank already containing N2 at 2 atmospheres and O2 at 1 atmosphere until the total pressure within the tank is 4.6 atmospheres. What is the partial pressure of the CO2? Okay, so we always want to start by asking, what do we want? You can see that in this case, it's the partial pressure of CO2. So whenever we see that word partial pressure, that should be, we know we're dealing with a gas mixture. We know we have certain equations, this Dalton's law for partial pressures. So we want to be, that is a key word to key in on, partial pressure. When we ask what else are we given, we can see that there's a lot of pressure values given. A lot of times, one of the things we said previously was when you're dealing with gas laws, if you're asked for a pressure and you were given other pressures, that'd be a sign that you could use, say, a named gas law, Boyle's law, something like that. But one of the things you'll note here is that all of these pressures correspond to different types of gas. We had CO2 that we want. We're given an O2 pressure, an N2 pressure, and a total pressure. None of those are CO2s, implying that it's not some sort of consistent change of a sample of CO2. Instead, you're dealing with a mixture where everything has its own unique pressure. And so if we look at the pressures of N2 and the pressure of O2, because a specific gas is specified, that implies that those are partial pressures. They're not labeled up in the prompt as being partial pressures. It just says N2 at 2 atmosphere. But whenever you have a specific name, a specific type of gas at a particular pressure, that means that is a partial pressure. That is a part pressure associated with that type of gas in the mixture that you're looking at. And then the 4.6 atmospheres, that's after the CO2 is added. So that's the total pressure of the entire mixture, of the N2 and O2 you started with, plus the CO2 that you're adding. So we've got a lot of partial pressures. We put them together in Dalton's law. And so one of the things to note about Dalton's law is that the specific form is always going to be based on the number of gases in your mixture. So there's 3 in this case. You would add those three partial pressures, N2, O2, and CO2, to determine your total pressure. Okay, so let's go ahead and solve it. We set up our Dalton's law equation. We know that what we want is, we add up all the partial pressures. We had 3 gases, 1, 2, 3. So they each get their partial pressures included in the equation. We're always going to want to make sure that we include all the types of gases that are in our mixture. Now what I want to do is I want to solve for the pressure of CO2. So what I'm going to do is I'm going to just subtract this side, these 2 pressures, onto the other side of the equation, isolate out the pressure of CO2. And then I plug things in. The total pressure was 4.6 atmospheres. The N2 pressure was 2 atmospheres. My O2 pressure was 1 atmosphere. And then I get an overall pressure of CO2 of 1.6 atmospheres. One of the things to note that you'll see when you're doing this process, all of these do need to be the same type of pressure unit. Here they're all atmospheres. That works. You can, but it doesn't have to be atmospheres. It just can be any single pressure unit, bar, torr, millimeters of mercury, pascals, whatever it is. But they all have to be the same. In this case, they're all atmosphere, works out, you get the 1.6 atmospheres.